Hello, welcome to my technical talk about UUIDs in Postgres. And there was a big change in Postgres 18. Native support for UUID version 7 was released, and this helps a lot with primary keys. So let's dive into this topic a bit deeper. I work for a German company called Credative. We offer support for open source products, and Postgres is one of our biggest topics. So, what will be this talk about? I will explain what the UUIDs are, uh, what are the issues using UUIDs as primary key in Postgres, and why version 7 is actually a big deal, and I will also show differences between using UUID version 4 and UUID version 7. So what are these UUIDs or universally unique identifiers? And those are generally 128-bit long numbers, like generally 16-byte integer value, which are for visualization represented as 32 hexadecimal digits with 4 dashes for better readability. There are several versions of UUIDs. We usually hear about UUID version 4, which are completely randomly generated, and now there are many articles about UUID version 7, which are time-ordered with millisecond precision. But there have been also other versions of UUIDs, and some of them are still actively used. Uh, Especially UUID version 1, which was time-based and included MAC address of node. Those are still quite often available in browsers for generating these universal unique identifiers in web services. Here some schemas. Here is a schema of UUID version 1. Here is UUID version 4. That format of UUIDs with those hyphens or minus signs is actually useful for readability, because in that third group, first digit means version of UUID, and in fourth group, first digit or at least 2 or 3 upper bits mean variant of that UUID. If you play Minecraft, then you already are using UUIDs every day, and this is nothing new for you, because in Minecraft, every object is identified by UUID, and these UUIDs ensure uniqueness of these items across servers and sessions. Also, users have their UUIDs. So in special command mode of Minecraft, there is /UUID command, which can show you UUIDs for whatever entities are available. Here is a screenshot from such command mode. And link to article which explains more. UUIDs actually were created for distributed applications for microservices architecture, and idea was that these identifiers should be generated by clients, and there was mechanism needed which would ensure that these identifiers are really unique. And this is also the reason why UUID version 1 had that MAC address of node embedded in in that in that value because it was also meant as identifier of that specific node. And UUIDs proved their validity and are used more and more across systems. In Postgres, when we talk about primary keys, we shall understand that primary key is a unique value which identifies uniquely records in table. They are implemented as unique index on that particular column, and data type and length of the data type we choose for that primary key can strongly impact performance and scalability. And also primary keys are used as reference keys for foreign keys for data integrity. So it is necessary to have values which will do not hurt joins or searches and so on. So common choices for primary keys in Postgres are either called serial or big serial, which are actually just aliases for integer and big integer, which are generated automatically from sequence. In newer versions, we have in Postgres this integer or big integer with clause generated always as identity. Difference is that here with serial and big serial, and that sequence is explicitly mentioned in default value, and there have been issues with granting permissions to tables. With this serial, big serial, we had to grant specifically also access to that sequence. With this identity column, sequence is hidden behind the scene. Default value is described as generated always as identity. And when we grant table, this hidden sequence is granted automatically with that table. But for some applications, and even that big integer was not enough, and therefore people start to use the UUIDs. Unfortunately, older versions than 7 had all those problems, which I will show you in future slides. There are also some anti-patterns for choosing primary keys in Postgres. First of them is composite key with many columns. This is really bad for performance because it increases index size and complexity, because B3 entries in Postgres, they store full key values. So if these keys are very large, there are only few items on that leaf page in index, and it means that those B3 indexes are getting bigger and more complicated. And using index search on composite keys with large keys means a lot of I/O lookups. This, of course, slows down joins, lookups. Foreign keys must repeat the whole key. Also, partitioning on such a complicated primary key means that all these columns must be included into partitioning key. Another anti-pattern for primary keys is usage of mutable primary keys, meaning emails, usernames, login names, whatever values which can actually change over time. And their change would require updates to the primary key column and cascading updates to foreign keys. So, when we look at usual choices for primary keys in Postgres, there's integer and big integer IDs. They are simple and efficient, but problem is that can easily lead to collisions in distributed systems. For example, like multi-master replication or just gathering data from several source databases and putting them together into data warehouse can be also complicated. And problem also is that their ranges can be too small for really large data sets. UUIDs, they provide much larger address space and solve those collisions in distributed systems automatically and can be generated on the client side, but existing versions, older than version 7, had issues with performance, especially UUID version 4, which is completely random value, leads to really badly fragmented indexes, and I will show you. A few words about UUID uniqueness. So UUID is identifier 128 bits long, meaning 16 bytes. This means that we have 2 to power 128 options, which is roughly about 3.4 times 10 to power 38 unique values. So yeah, this is really a huge number. So probability of collision is extremely low, and Wikipedia calculates that for UUID version 4, probability of collision is 1 in a billion after generated 10 to power 14 UUIDs. Again, this is practically zero for our real-life systems. There are some known issues with some non-unique UUIDs, but this is not because of problems with UUIDs. This is because of issues with rewriting them. There was, for example, this issue with this particular UUID. As you can see, this is quite arbitrary, artificially constructed UUID, which actually does not have even proper version, because here we have 0 and here also 0. And this UUID was used as basic UUID for some gigabyte motherboards. And during manufacturing process, there was some issue with rewriting this default UUID. So many motherboards had actually the same UUID, but it was not issue of algorithm, it was issue of that manufacturing process. UUID is for better readability, represented as text string from those hexadecimal digits, and standard format for representing is this 84412. Here typical example showing how it looks like, and as I already mentioned, first digit in the third group means version. So here we will really see like number 4 or number 7 or other numbers. And First digit in fourth group means encoded variant in top 2 or 3 bits. And those hyphens, they improve readability. And if we look at documentation of UUID, they mention these two special UUIDs. First of them is nil UUID, so it consists from all zeros, and maximum UUID, of course, consists from all F hexadecimal numbers. And we can often also see this representation of UUID, which might look somehow complicated, but this UUID, this is one UUID, which is actually represented as 8 hexadecimal digits, or 32 bits in one line. So 32 times 4 is 128. And this is how they describe it in documentation. I don't think this is exactly nice for readability, but yeah, just for explanation what this presentation means. And now, what about UUID version 7? This is actually game changer for many reasons, because it contains milliseconds here in these first two groups. There is this Unix epoch value in milliseconds embedded here, and remaining part of that UUID is random. So consequence of this construction of this pattern is that generated UUIDs are actually ordered sequentially by time. Yeah, there is one small gotcha with this. This UUID version 7, and we can recognize it from this digit. This UUID actually exposes timestamp when it was created. And if we get the whole sequence of those UUIDs, we can analyze time difference between records. Yeah, for some applications, it could be something they should consider if it is safe or not for them. But for a majority of applications, there will be probably no issues with this. How databases store UUIDs? This is actually a very interesting question. And we are lucky that Postgres stores UUIDs natively, really as 16-byte binary value. Some databases, they don't take UUIDs as something special, and they store it simply as 36 character text with all of those hyphens. So like Elasticsearch, CouchDB, BigQuery, and they handle it as text. Other databases, they use either binary, raw, or blob type with dimension 16 bytes, but they don't have any specialized UUID data type. Others have this native 16-byte UUID type, like SQL Server, Cassandra, MongoDB, CockroachDB, and of course Postgres. So when we look at native Postgres UUID support, we can find it in source code in this file src include utils file uuid.h. And here is defined structure pguidt as unsigned char data 16 byte. C language handles this character, char, or whatever pronunciation is, as 1 byte of opaque data, meaning data have no specific type interpretation and must be interpreted by procedures which actually process these data. And Postgres offers this function for generating a UUID version 4 and new function for generating UUID version 7. And also two other functions are useful. First of them extracts version from that UUID, although it is readable when we see it, but if we would want to use it in where conditions and queries. And second function extracts timestamps from those UUID version 7. So let's now dive deeper into performance differences between using UUID version 4 versus using UUID version 7 as primary keys in Postgres tables. So I created this testing example. I have two tables. Both of them have just two columns. Column ID is type UUID is primary key. And this second column is a big integer generated always as identity. So this ord as ordinary number, it preserves insertion order for our testing purposes. And when I create these two tables, I insert 1 million of records. I have performance tests with more records, but for these purposes of analysis, this is good enough, and it's also reasonably quick, because as you will see later in slides about benchmarking, that UUID version 4 is quite slow. But let's dive first into analysis. So now when we have 1 million of records inserted, let's look at order of rows. UUID version 4 is completely random, so it means if we try to order table based on UUID version 4, those values are completely randomly distributed across the table. So here is example from my test. When I select first 20 rows, which are ordered by UUID from that table with UUIDs version 4. And for better readability, here is this row number window function over all records. So we will see here ordinary number of that row. And here in that ORD column, we see ordinary number of insert. And here is our well-known ctid, which means data page number and and ordinary number of that tuple inside that page. So you can see that when we go by order of those UUID version 4, we are jumping completely randomly all over that table. Those numbers are quite badly scattered. So if we would actually address specific record from that table based on this UUID4, you can see that this will mean a lot of random I/O. On the other hand, when we look at table with UUIDs version 7, we can immediately see how nicely they are ordered sequentially in the table. So here is again that window function showing us row number. Here we have those UUIDs version 7 inserted into table, and voila, you can immediately see those timestamps, and things are going in nice order. We are reading page by page, tuple by tuple. So completely different situation. We can also look into statistics because we used vacuum analyze on both tables to collect statistics about that table. And there is this column called correlation, which shows how well are those tuples physically ordered on that in that table, how well they match index order. So when we select correlation, we can immediately see that in a table with UUIDs version 7, there is a perfect correlation. Correlation is 1. Meaning correlation is in perfect order, going from lowest to highest value in ascending order. But when we look at correlation of ID column in table with UUIDs version 4, we can see that value is almost 0, so which means that there is no correlation of those values. So they are completely random. And let's now look into indexes to understand what is the main issue with UUIDs version 4. So here I calculated some statistics from those indexes and I used this pgstat_index function, and let's analyze it. So here is primary key on IDs based on UUID version 4. Here is primary key on ID with UUID version 7 values. So what we can immediately see here, this third line is important. It is index size. So when we look at index sizes, we can see that primary key index on UUID version 4 is around 26% bigger than on UUID version 7. We can also see that it has more those leaf pages with tuples. So again, difference is around 26%. So here are like 4,800 leaf pages for UUID version 4 versus 3,800 leaf pages for UUID version 7. We can also see that those leaf pages have a lower density. There is this default fill factor 90%, and UUID version 7 actually uses that fill factor almost fully. And average leaf density of that primary key index on UUID version 4 is only around 71%. And fragmentation of primary key index on UUID version 7 is 0, but leaf fragmentation of primary key on UUID version 4 is around 50%. Yeah, well, those are first numbers showing big differences. But let's look even deeper. Let's try even deeper statistics. So here is some query which I used for those stats. And this is what I got. So here is that UUID version 4 B3 index. Here is UUID version 7 B3 index. We already looked at count of leaf pages. And let's now look at minimum number of tuples per page, maximum count of tuples per page, average, and also if those leaf pages are following one after each other or they are actually random. So what we can see here that primary key index on UUID version 4 has average count of tuples per page around 200, which means when we compare later those numbers that average density of those pages is smaller than those 90%, that's 71, because here we have density 90%, which is this number 262 tuples per page. So you can see that per average, it has difference is 60, around 60 tuples per index page. And when I dive deeper into those numbers, this 146 count of tuples per index page means that these pages are half empty. What is interesting here that some pages are almost full above that default fill factor 90%. So it was very interesting finding that actually Postgres tries to use those pages, if necessary, even above that fill factor, or those, although the amount of these pages is not that big. Here, for UUID version 7, practically all pages have the same count of tuples per page, this 262. Only the very last page is not full. So this is why also that average is almost the same as maximum count of tuples per page. And we can see here that in that B3 index for UUID version 4, those pages are completely randomly distributed over the index, but here in primary key index for UUID version 7, almost all pages follow each other. Yeah, I will show you details. So this is that chain of leaf pages for UUID version 4. Every B3 index has 0 page as root page, and one of those first pages is also so-called internal page, which actually contains pointers to level of pages. So when I list first 20 pages, not of course using that root page, you can see these pointers to previous and next page. So here I have first leaf page in that B3 index. Previous page is page 0, meaning root index, but next page is page 3744. In normal sequentially generated index, all pages follow each other. And this is exactly the situation what we see in B3 index for primary key based on UUID version 7. Here, first leaf page goes from root page and addresses second page. Second page shows that previous page is page 1 and next page is page 4, because third page is this internal page with pointers. But when we jump at page number 4, we are back in that sequence. So page 4, previous page is page 2, and next page is page 5. And as you can see, all these leaf pages are sequentially ordered one after each other. All of them, well, let's not look at this internal page because this is special, but all those leaf pages, they have 262 tuples per page. When we go back to this B3 index for UUID version 4, you can now see that complete randomness. We are jumping randomly, crazily through the structure of the index, and also number of tuples which are stored on that page is oscillating quite rapidly. These pages with 150 or 140 something tuples, they are practically half empty. So now we can see how badly fragmented this index on UUID version 4 is, and how nicely ordered and compact is this index on UUID version 7. We can also try histogram to show it better. So here is histogram buckets by 10 from 100 to 299. And when we calculate it and show only those buckets which contain values, index for UUID version 7 is very nice. Practically all pages are in one bucket because they all have those 262 tuples per page, meaning fill factor 90% is used here, and only that one last page has 109 tuples and therefore is in that first bucket. But when we look at index for UUID version 4, we can see how badly this index is actually used. So here, these first two buckets, they mean practically half empty pages. Here is bucket for fill factor 90, and we can see that there are pages which actually exceed that fill factor, and empty space on them is getting smaller and smaller. So Postgres tries to use that page as much as possible to avoid the necessity to split that page. And again, you can see how badly fragmented and how badly used is space in that B3 index. I mentioned that there is a small issue with this UUID version 7 because they expose insertion time. And there is a special function, UUID extract timestamp in Postgres 18, which we can apply on those values to extract that timestamp. And here is example from first 5 rows. How it looks like. And looking at performance of queries, let's compare query plans. So I ran explain analyze with buffers on those queries which select all columns, all records from those tables ordered by that ID. And difference is immediately visible. First of all, execution time of that query on UUID version 4 is almost 3 times bigger. And execution time of query on UUID version 7 is much smaller. And in both cases, I actually had already warm cache, so there was no big necessity to read so many. Although here we see reads, but we can also see that for extracting those records for UUID version 7, Postgres needed only relatively very small number of reads from shared buffers and bigger reads from disks. But here with UUID version 4 and it's completely random disk I/O, you can see how many hits into shared buffers had to be done, like 1 million. Here, when we put these numbers together, we get like 10,000. And here we have 1 million, meaning 100 times bigger amount of hits. So it also explains not much longer execution time. Yeah, still talking about milliseconds, but yeah, difference is quite big. And there is also a big difference in insertion time. And for these purposes, I actually used, I would say, naive benchmark with 50 millions of rows. And that is actually mistake. I originally wanted to test 100 million rows, but it was so incredibly slow for UUID version 4, so I had to lower that amount to 50 million rows. And here you can immediately see why. I created empty tables again, dropped all tables, created empty tables, and inserted first uh, 50 millions rows into empty table, and after it repeated it to insert again 50 million rows into existing table with those previously inserted rows. And I did it separately for both tables to not influence each other, of course. But results were like incredibly different. So you can see that insertion into empty table with UUID version 7 took only like 1 minute and 46 seconds. But with UUID version 4, the same 50 millions rows took like 20 minutes and 40 seconds. It's, I don't know, 15 times or more times more. And when I repeated that insertion into table which already had those 50 million rows inserted, I actually got even bigger difference. So with UUID version 7, insertion time was almost the same, slightly slow, slightly quicker. I don't know why, but the difference is negligible, statistically absolutely negligible. But with UUID version 4, that insertion time was like more than 2 times bigger. It took 46 minutes and 16 seconds to insert another 50 million rows into table with UUID version 4. And you can see differences in sizes of indexes. Tables are, of course, still the same because they have practically the same content, meaning 16 bytes UUID and 8 bytes big integer in each record, plus those system columns. But you can see growing differences in indexes. So this even very naive benchmarking with just inserting these batches of 50 million rows is showing that huge difference. So this is the testimony to performance issues with UUID version 4. And this is the last slide, so let's summarize it. UUIDs are amazing because they provide an enormous identifier space and global uniqueness. But traditional UUIDs version 4 are completely random and cause severe index fragmentation. They lead to larger indexes and very poor insertion performance. UUIDs version 7 values are time ordered, they improve index locality, everything is nicely ordered. They reduce index size, pages are not splitted because they are just added one after each another. They greatly improve insertion performance, and Postgres 18 includes this native UUID version support, so it makes things very easy for us. But we must remember that these UUIDs version 7 expose insertion timestamps and therefore may not be suitable for all use cases. And this is everything I wanted to show you today. And I will now stop recording.